First, let's get a high-level definition of duration. The duration of a bond measures the sensitivity of the bond's full price to changes in interest rates. Broadly speaking, there are two categories of duration: yield duration and curvature duration. Yield duration measures the sensitivity of a bond price to changes in the bond's yield to maturity, whereas curve duration measures the sensitivity of a bond price to changes in market interest rates. Just to emphasize the point here, you might recall from the previous chapter that the YTM of a given bond depends on our reference rate or the benchmark rate. Let's say we are considering the YTM of a 5-year corporate bond, and a comparable government bond has a yield of 5%. The YTM on the corporate bond is 6%, which means that the spread is 1%. With yield duration, we will consider the changes in the overall YTM, which includes the spread. With curve duration, we will only consider the changes in the interest rates of government bonds, which is our starting point over here. Under yield duration, the first basic type of duration that we'll consider is Macaulay duration. Macaulay duration is a weighted average of the time to receipt of the bond's promised payments, where the weights are the shares of the full price that correspond to each of the bond's promised future payments. Here we are considering a 10-year 8% annual coupon bond, and these are the various cash flows. This represents the present value. So the first cash flow is 8, which is after one period. The present value is 7.24. The second cash flow again is 8. The present value is lower because this second coupon payment comes later. If we add up all the present values, we have 85.50, which is the price of the bond. The weight of each cash flow is that cash flow, in this case 7.24, divided by the total present value, which is also the price of the bond, and the weight therefore for the first one is 0.08475. You multiply the two and you get this number. Then you add all these numbers and you get 7. The Macaulay duration then for this particular bond is 7. And notice that this Exhibit 2 from the curriculum nicely illustrates the definition of Macaulay duration. The Macaulay duration can also be calculated using this formula. To be super diligent, you can memorize this formula, but I think that understanding the interpretation of Macaulay duration is much more important than memorizing this formula. Nevertheless, if you have time, then go ahead and do learn the formula. Next, we talk about modified duration. Modified duration is simply the Macaulay duration divided by 1 plus R. R is the YTM, or the yield to maturity for the bond. Modified duration provides an estimate of the percentage price change for a bond given a change in its YTM. So this is the interpretation of modified duration. If we take this interpretation and express it as a formula, this is what we have. The percentage change in the value of a bond, and this is actually the full price of the bond, is equal to the modified duration times the change in yield. Let's say that the modified duration of a bond is 4 and the yield changes by 0.5%. Then what is the percentage change in the value of the bond? That is going to be 2%, and we can see that over here. 4 multiplied by 0.5% is 2%. So the percentage change is 2%. You might wonder why we have the minus sign. The reason is if the yield increases by 0.5%, then the change is actually going to be negative 2%. In other words, the price of the bond goes down. The modified duration provides a linear estimate of the percentage price change. Notice that if the yield went up by 1%, then the percentage change in price of the bond would be minus 4%. So this formula is actually a linear approximation. Make sure that you understand the interpretation of modified duration and Macaulay. And just to refresh your memory, with Macaulay duration, the duration is the weighted average of the coupon payments or the cash flows. So weighted average of the time to receipt of bonds promised payments. And here the interpretation is that modified duration provides an estimate of the percentage price change for a bond given a change in its YTM. Next, let's understand approximate modified duration. And here is the formula for approximate modified duration. The interpretation can be understood by looking at the price yield curve, and this approximate modified duration at a given point on this graph is simply the slope. Here we have price on the y-axis, YTM on the x-axis. This picture is something you've seen before. For a regular straight bond, it is showing the relationship between price and YTM. Let's say that at a given point in time, we have a yield of 10%. This is the YTM. And let's say that this is the price when the YTM is 10. PV minus is the price of the bond when the yield goes down by some delta amount. Let's for simplicity say that this is 1%. So if the yield goes down to 9%, then there is a certain price of the bond that is given by this number. If the yield goes up from 10% to 11%, then the price of the bond is PV plus, which is given by this number. The approximate modified duration then is this minus this, so that's PV minus PV plus, this distance divided by 2 into delta yield. Delta yield in this case is 1%, which would be 0.01 in decimal terms, multiplied by the value initially. So this central value, which is 100. To plug in the numbers that I am using, PV minus, let's just actually use numbers for PV minus and PV plus. Let's say that PV minus is 105, and that is going to be more than 100, minus PV plus, which is this number. Let's say that that number is 97, and then 2 multiplied by delta y. Delta y or delta yield is the change in each direction, which is 1% in my example, or 0.01, multiplied by PV0, which is 100. When you get the answer to this, you will have the approximate modified duration of this particular bond. You need to memorize this formula. The interpretation is that this approximate modified duration is simply the tangent to the price yield curve. Now let's take a look at example 8. For this question, I'll skip some of the details and get straight to the approximate modified duration. Remember, the formula for approximate modified duration is V minus V plus over 2 into delta yield into V naught. So this is the actually I've used V here, which is the value of the bond. V minus is the value of the bond when interest rates go down by a certain amount. And when we do the calculation, and the curriculum shows the calculation, we get 81.12. So that's what's plugged here, minus the plus value. Plus means that interest rates go up. Here the value of the bond is actually lower, 79.89, divided by 2 into change in yield. The change in yield is 5 basis points, which is the same thing as 0.05%, which is the same thing as 0.0005. The number here has to be in decimal, and then multiplied by the initial value, which is 80.50. When you do the calculation, you should get a duration of 15.368. This is the approximate modified duration, and the interpretation of this number is that if the yield changes by 1%, in other words, let's say the yield goes from 5.14% to 6.14%, then approximately speaking, the price of the bond will come down by 15.4%. So far we have focused on straight bonds or conventional bonds. These are bonds where the cash flows are known, both the timing and amount of cash flow is known, and these bonds have a well-defined yield to maturity. The duration measures that we have talked about so far are yield-based duration measures, and they work for bonds where the cash flow is known. But what about mortgage-backed securities and bonds with embedded options? These bonds do not have a well-defined yield to maturity. The reason is that cash flows depend on external factors such as interest rates, so there is no well-defined yield to maturity. Therefore, the yield duration statistics or measures that we've talked about so far, such as Macaulay duration, modified duration, and approximate modified duration, do not apply. We need another duration measure, and this is where effective duration comes in. The effective duration of a bond is the sensitivity of the bond's price to a change in a benchmark yield curve. So if our benchmark is the government yield curve, then effective duration is measuring the change in value of a given bond when there is a change in the benchmark yield curve. And the formula is given right here. This should look quite familiar because the only thing that is different between this and the formula that you saw earlier is this expression over here. We are looking at a delta or a change in the benchmark yield curve. Let's do example 9 now. This is a long-winded story, but it boils down to the use of this formula that we discussed on the previous slide. The effective duration is given by the value of the liabilities if the interest rates go down minus the value of the liabilities if the interest rate goes up, and then divided by 2 into delta into the initial base value. When you plug in the numbers, you get 5.49. So this is the effective duration. Properties of bond duration. The Macaulay and modified yield duration statistics for a traditional fixed rate bond are functions of the input variables, and those input variables are the coupon rate, the YTM, the number of periods to maturity, and the fraction of the period that has gone by. Let us start with this item, the fraction of the period that has gone by. So what is the relationship between Macaulay duration and the fraction of the period that has gone by? I will reproduce this formula for Macaulay duration, and let us assume for a minute that YTM, as denoted by R, is constant. If that is constant, then the expression in these brackets is constant. The only thing that is changing is small t over big T. And to refresh your memory, big T refers to the overall time between coupon payments, and small t is where we currently are. So as time passes, small t increases from 0 to big T. You can also think of it as follows. As t increases, we are between coupon payments and the time to maturity is coming down. In other words, as t increases, we are moving from right to left. If you think of these 2 points as the ends of a given period, then as we are moving in this direction, that is the same as saying that small t is increasing. Notice that when small t increases, this expression is going up, and since Macaulay duration is this constant minus an increasing number, the Macaulay duration is coming down. It comes down until small t is equal to big T, and then small t resets to 0, so we jump up, and that is what gives this sawtooth shape. So that is this relationship, the relationship between Macaulay duration and fraction of the period that has gone by. This is Exhibit 7, and it shows the relationship between time to maturity and Macaulay duration. If we take a 0 coupon bond, then bonds with higher time to maturity have a higher duration. In fact, this is a 45-degree line. So a bond which has a time to maturity of 5 years will have a Macaulay duration of 5. The period of the bond, or the maturity time of the bond, is equal to the Macaulay duration for a 0 coupon bond. In general, you see that the higher the maturity, the higher the duration, and that makes sense because higher maturity would imply greater interest rate sensitivity. The awkward item over here is the discount bond, and the curriculum gives an explanation for why there is this potential bend at the end. If you have time, you can go through that, but I don't think it is a very important point. The larger point to recognize is that by and large, as time to maturity increases, the interest rate sensitivity, or the Macaulay duration, goes up. For a perpetuity, the Macaulay duration is given by 1 plus R divided by R. The next item is the relationship between the coupon rate and Macaulay duration. As you can see, if the coupon rate is high, then the duration, or the Macaulay duration, is less, and that is visible over here because 0 coupon is the lowest possible coupon rate, and here the duration is the highest. As the coupon rate goes up, the duration comes down. You can also think of this as follows. Macaulay duration is a weighted average of the cash flows, and with a high coupon rate bond, you are getting more money back sooner. In any case, the key relationship is right here. If the coupon rate is high, then the duration will be lower. And finally, let's look at the relationship between duration and yield to maturity. And I think it is easier to understand this relationship if we look at the price and YTM curve. For a conventional bond, this is what the price YTM relationship looks like. And notice that the interest rate sensitivity, which is measured by the slope, is relatively high at low YTMs, and the absolute value for the slope is relatively low when YTM is high. So there is an inverse relationship between YTM and duration. High YTM means relatively low duration and vice versa. Let's take a look at example 10 now. This is a fairly mechanical example where you are supposed to use this formula. Let's take bond A. Given that we are supposed to do a 1 basis point change, recognize that 1 basis point is equal to 0.01%, which is equal to 0.0001 in decimal. So that is what you will plug over here. PV naught will be this number. PV minus would be the bond price if the interest rate goes down by 1 basis point. So when you do discounting, you would have to use a rate of 19.99%, 1 basis point less than 20%. When you do your calculations for PV plus, you will have to use a discount rate of 20.01%. Using these numbers, you come up with PV minus PV plus, and for bond A, the answer is going to be 4.768. This is the approximate modified duration for bond A. For bond B, using the same logic, the approximate modified duration will be 5.169. And for bond C, the answer will be 5.063. The numbers are fairly similar, but note that the greatest interest rate sensitivity is with bond B. Even though bond B is a 20-year bond and bond C is a 30-year bond, and this illustrates the fact that with a discount bond, we could actually have a shape like this, where duration is on the y-axis, time to maturity is on the x-axis. This example demonstrates the fact that a 20-year discount bond could have a higher duration than a 30-year bond. And hopefully it is obvious that all these are discount bonds because the coupon rate is much lower than the YTM. Here we are looking at the price yield relationship of a callable bond, and notice that on the x-axis we have the benchmark yield. Over here in red we have a non-callable bond or a straight bond, and this is the regular price yield relationship that we have talked about before. With a callable bond, the relationship is a little different. If a bond is callable at, let's say, 102% of par, say this is par value, then the bond price cannot possibly exceed 102% of par. As interest rates fall, the maximum the bond can be worth is 102, which means that this bond will show negative convexity. As opposed to a regular straight bond, which is convex, a callable bond will show negative convexity when interest rates are low. You can also see that the interest rate sensitivity is low. For a straight bond, this slope, which is an indication of interest rate sensitivity, is relatively high, but for a callable bond, the interest rate sensitivity is relatively low. At very high yields or high interest rates, there is not much difference between the non-callable bond and the callable bond. The reason is that at high interest rates, the probability of the bond being called is extremely low. Exhibit 9 in the curriculum shows a puttable bond. With a puttable bond, at low interest rates, there isn't much difference between a regular bond and a puttable bond. That's this region. And the reason is straightforward. At low interest rates, investors are not likely to put the bond back in the lap of the issuer. So investors are likely to hold on to the bonds and not return them to the issuer. But at high interest rates, that is where the difference comes in. At high interest rates, investors are more likely to return the bond. That's why there is a difference. Also note that if a bond is puttable, that in a sense puts a floor on the price of the bond, and that floor keeps the price of the puttable bond above the price of the non-puttable bond. The distance between the two curves represents the value of the put option. On the previous slide, this distance represents the value of the call option, and this is something that we have seen in the previous reading also.